Hello and welcome back. Today we're going to reintroduce you to the solar system. Now that you're armed with a good deal of knowledge, especially about the scientific method, about Kepler's laws, about Newton, the work that Galileo did, a bunch of physical principles, things like motion and gravity and forces, or forces like gravity, I should say. And you also have a general idea of how the Earth moves through the solar system, where it is in the solar system, where it is in the universe, as a matter of fact. And armed with all of that, we're now going to go back in, take a look at the solar system and its various components in far more detail. Now, I do something slightly more unusual, where today we'll talk about the solar system and its formation and things like that. And we'll jump right away into the most insignificant parts of the solar system, or depending on whom you ask, which is the gas, dust, rocks, and comets. Because I like to do it that way, because those are things known to be left over from the solar system formation. And so they're kind of tied in some ways. And so that's why I like to treat them together. And then we'll go into things like Earth in a lot more detail, then the moon, and Mercury, then Venus and Mars, and we'll go on to the big planets, Jupiter and Saturn, Uranus and Neptune. And finally, we will talk about the moons of the big planets and why they might be interesting. And then, of course, the big finale is the sun itself, which we've been ignoring for a while, the solar part of the solar system. And then we'll talk about extrasolar planets as well. So that's the general roadmap for the next few weeks. But all of this so far was basically setting up background. And now finally we can dive into what this course is all about, which is solar system astronomy. You didn't know that it was, sneakily trying to get you to absorb all this other stuff before you got here. But hopefully you have, and that'll make you understand this material or appreciate it with a little more depth, and even things like articles about the solar system that you get to see with a little more of a critical eye and a little more depth. In one of the previous lectures, we talked about an analemma, which is a picture taken of the sun at the same time, at the same location on different days. And you get this figure 8 curve, which is pretty cool, that both is a result of the Earth's axial tilt. So the sun seems to move up and down in terms of elevation in the sky at a given time. And then it traces out this figure 8 pattern because of Kepler's laws, because the Earth is slowing down and speeding up as it orbits the sun. So the sun is sometimes ahead of what we would consider noon, and sometimes it's behind, and so on. And so this is a moonalemma. It's in the Astronomy Picture of the Day website, and it just popped up. And it's worth looking at and taking a look at the description. And there are some tricks over here, though, because with the moon, you can't take a picture at the same time every day, because you might have noticed from your own personal experience that the moon has different setting and rising times. So because it's moving in orbit around the Earth, you have to wait an extra 50 minutes and 29 seconds from one day to the next to basically capture the moon at the same position. And so whereas an analemma is done over the course of one Earth orbit around the sun, this picture was taken over the course of one moon orbit around the Earth. So the analemma, you have to wait a whole year to take it and pick, say, maybe 8, 10, 20, 30, however many days you want, and go out, hope you have good weather, and take a picture of the sun. With the moon, you can do this on 30 consecutive days, but just go out 50 and a half minutes later every day to take a picture of the moon. So this is over one lunar month, and it also traces out an analemma-like curve because the moon also, because the Earth's tilt is, the moon's orbit around the Earth is tilted. If you remember back from the eclipse class, there's a 5-degree tilt, which is why we don't have eclipses every time the moon gets into every time there's a new moon and there's a full moon. And so you also need to have good weather over here, but you can finish this in about 30 days as opposed to having to wait a whole year. So I thought this was kind of cool, related to our analemma, related to the material that we just finished about eclipses and the moon's orbit and so on, and sort of puts that all together nicely. It's a lovely photo. One thing I want you to think about is you'll notice in the figure 8 there are what should be around 3 photos missing. So there is no actual figure 8 crossing point like you see in the sun, and I want you to think a little bit about that and figure out why there is no crossing point. And it, of course, has to do a little bit with where in the moon's orbit, or in the set of moon's phases, the moon is as seen from Earth. Okay, so that's one cool thing I encountered. The other thing is, a couple of months ago, this telescope called the Daniel K. Inouye Solar Telescope, or DKIST as it's easier to say, has opened up on the peak of Haleakala in Hawaii. So yet another, we talked about the 30-meter telescope on the peak of Mauna Kea, which is on the big island, Hawaii. This is the neighboring island, but also an old volcano, Haleakala. And it's a telescope that has opened up on that peak as well. I don't think there is not as much controversy about Haleakala as there is about Mauna Kea. Not that I'm aware of, at least. So why is this cool? Well, this is a solar telescope. So this operates during the daytime when the sun is up, as opposed to our regular telescopes that we're used to, which operate at nighttime when we want to observe anything except the sun. And it's the largest solar telescope ever built so far. It has a 14-foot wide primary mirror. So the largest existing solar telescope is 2 feet wide. So again, some things to think about. I was about to say reflect upon from your prior telescope classes, what type of telescope it is. What happens when we go from a 2-foot wide mirror to a 14-foot wide mirror? What are the benefits it gives? Does it give us? But of course, the other thing is that, oh yes. So one thing to think about is, again, sighting this telescope. Why is it up on a mountain? Look at what the mountain looks like, and so on. What are the structural benefits of having a mirror here as opposed to, say, a refractor-based telescope? And yeah, there's a bunch of space-based solar telescopes as well. So what is the benefit of having this, for example? Now, the other thing to think about is, well, why did they stop at 14 feet wide? Why didn't they go on to, 20 feet wide or so on, like some of the big reflector telescopes that we have? I want you to think about what we're imaging over here. So if you've done experiments where you've held a magnifying glass and hopefully not tried to burn a living creature, but try to burn a hole in a piece of paper, for example. Imagine, so those magnifying glasses tend to be, I don't know, a couple of inches wide maximum. And you can already create some damage in paper with a smallish magnifying glass like that. Now imagine a 14-foot wide magnifying glass focusing the rays of the sun to a point. What's going to happen? Okay. So cooling is a big issue in a telescope like this. But some of the cool things about this, that even this telescope uses adaptive optics, which we learned about. So there's the adaptive optics mirror on the right side, or at least the base layer of it. So the reflective coating will be applied on top of it. So these are the pistons, the 1600 pistons that will be moving up and down 2,000 times a second to change the shape of the mirror as it is imaging the sun. So one thing about daytime is that the sun's heat causes more turbulence in the atmosphere than at the nighttime. So adaptive optics is even more necessary for daylight observing than it is for nighttime observing. And of course, here's something about why they picked Haleakala as a site for this telescope. And so with this adaptive optics system, now they can image the sun in absolutely unprecedented detail. So the first few images that they released, one of them is shown on top, and the state of Texas is shown in there for comparison. So each one of those convection cells, as we learn later on when we study the sun, is the size of the state of Texas. and that is amongst the best resolutions. And the features that we can see are down to the size of the island of Manhattan, for example, all because of this adaptive optics system. And so now with the mirror in place, that's what it looks like. So the vertical shiny disc in the center of the image is this mirror fully assembled. So now you can see the reflective coating. The pistons are behind it, and you can see this whole host of wires, because all 1,600 wires are needed to individually control each of those pistons. So anytime you go to a telescope, and I hope you do, it's an amazing experience. I hope you will take the opportunity to then ask for a tour of, say, the adaptive optics system, and you can seem really, really smart or perceptive or whatever by looking for the component in the adaptive optics system that has A, the shiny surface, and B, has tons of wires going into the back of it, and ask the person who's giving you the tour, hey, tell me a little bit about this deformable mirror right here. And they'll probably look at you very impressed, going, whoa, how did you know, A, that was a deformable mirror, and B, how did you even know what it is and what it does, and so on. So there's a tip next time you happen to be touring a telescope, or you're at a cocktail party and this sort of thing comes up in conversation. It happens at the ones I go to. I don't know about the ones you guys go to, but maybe you should start going to the ones I go to, for example. No, I'm just kidding. Okay. Right, like I said, we are going to be reintroduced to our old friend, the solar system. So far, if you're not already sick of it, it should look like a friend. And here we are again. I put this picture up, I think, in the first or second lecture. And essentially, it gives you a comparison of, well, it gives you most of the components of the solar system that we're going to be studying. In fact, well, I'll say, except for comets, it pretty much gives you everything that we will be studying so far. So, and the main diagram is with sizes to scale. So the sun is huge. It's 10 times the diameter of Jupiter. And then Jupiter is 10 times the diameter of Earth, for example. So the sizes are to scale. And for distances to be scaled, there's a bar along the lower part of the diagram which shows you from the sun out to Pluto what the distances are like. And since it's so tight in the inner system, you can barely make out Mercury, Venus, Earth, and Mars. But they're there. So today, we will go through all of these components, give you a broad overview, go into some depth about some of these things. So we will talk about what looks like an obvious dividing line between the planets. The 4 inside planets look very different from the 4 outside planets. And the 4 outside planets can also be divided into 2 classes over there. Between the closest planets, it's my technical term of inside planets, and the giant planets on the outside, there's an asteroid belt. So we'll talk about what asteroids are. Each of the giant planets has a whole host of moons. So Jupiter and Saturn have on the order of 50, 60 moons each. In fact, Saturn is the current champion with like 80 plus moons. But that keeps changing as we discover more and more moons around these objects, as we get better and better at detecting smaller objects. We'll also talk about the Kuiper belt, which is to the extreme right of the image, where there's a lot of icy bodies left over from the formation of the solar system, which is why it's so cool to study. Pluto and its moon Charon is now considered a part of that Kuiper belt when it got kicked out of the whole exclusive planet ranks. We'll talk about a whole class of objects called dwarf planets. So Pluto is now the archetypal or the template for a dwarf planet. And most of the dwarf planets that we know about live in the Kuiper belt, and those are Eris, Makemake, and Haumea. One dwarf planet lives in the asteroid belt, which is Ceres. Now, that's the largest asteroid. It has 1/4 of all the asteroids' mass put together, and so on. And there's a few other interesting asteroids in there, like Vesta and Juno, and so on. We'll touch over those. Okay, so let's dive into this. The other way to look at the solar system is, and this is on this phenomenal, nerdy webcomic called XKCD. It's just 4 letters. X as in X-ray, K as in koala, C as in Charlie, D as in Delta. So xkcd.com. And this is another way to look at, since you guys now know about gravity, this is another way to look at the influence of various planets that they have. So remember I mentioned something about an escape velocity to get out of the gravitational influence of a planet. So just like electrons and their energy wells, since gravity also is a force and has energy associated with it, you can draw the equivalent of gravity energy wells for each planet. And so you get a sense of how much energy or force you need to get out of the influence of that planet. And as you can tell, Jupiter, well, the sun is huge, so you can't even see where the bottom of the sun is because it dominates gravity by far in our solar system. But this is to give you a sense of what kind of influence Jupiter has as well. And here's a tip. We might not be here on this planet, but for the influence of Jupiter. Jupiter, as we'll talk about later on, acts as a giant vacuum cleaner in the outer solar system and ends up sucking in or gravitationally drawing in a lot of objects that might end up crossing Earth's orbit, for example, and causing some damage over here. So it's actually good to have a giant planet like that, somewhat far away, but not too far away from us. And so you can see the outsized influence that Jupiter has. The depth of that well is about 2.5 times the depth of Saturn, for example. And there are some that have almost negligible gravity. So, for example, one of the moons of Mars, Phobos or Deimos, if you happen to be standing on those, you could throw a baseball and basically get into orbit around the moon. Or, a pretty strong jump, for example, could get you off the surface of the moon and you'd be able to escape the moon. So all the way from really puny amounts of gravity to enormous amounts of gravity that Jupiter has, for example, you have all kinds of different beasts in this solar system, and we'll go over those. So again, this is a repeat of the slide. We have a central star, pretty boring average star, which is actually good for us, which is in the boring average suburban parts of the galaxy, which is also very good for us. It is orbited by 8 planets currently, for which 3 rules have been proposed. And Pluto violated the last rule, so it got demoted to the dwarf planet status. But then they realized, oh, wait a minute. Well, so the discovery of Eris, which is in bold, caused Pluto to be demoted because it orbits in the same region in the Kuiper belt as Pluto does. It also has a highly elongated orbit that's out of the plane of the solar system and is roughly the same mass as Pluto. So they were like, well, should we make Eris a planet or should we create a different category of planet? And for now, they chose the different category. Now, adding planets is not without precedent. At one point, I think astronomers considered, historical astronomers at least, thought that there were at least 20 planets around. So every asteroid, for example, that they discovered, they would consider a planet. The asteroid belt was discovered because of slight perturbations in the gravity of Mars that couldn't only be explained by Jupiter, for example. And so they looked for a planet between Mars and Jupiter. They found Ceres and said, hey, this could be a planet, let's add it. And then they found hundreds and hundreds of more objects orbiting them, and then I think some amount of sanity prevailed, and they said, we can't keep adding all of these to the list of planets. We need to think about this a little more, and so on. Okay, so rule number 3 is violated by this set. There's about 5 official dwarf planets so far. There's hundreds of candidates that need individual confirmation. They're hard to see. They orbit pretty far out, all that stuff. The ones that violate rule number 1, and rule number 3, of course, by extension, are moons. There are about somewhere between 7 to a dozen, so 7 largish moons around various planets, the Earth included. There's 4 around Jupiter. There's 1 around Saturn that's really interesting. There's 1 around Neptune that's really interesting, and maybe even Pluto's moon is pretty interesting as well. So 7 to 8 interesting moons from just a size perspective. They're all, at least the first 7 are large, definitely larger than Pluto, and almost as large as Mercury, maybe even larger than Mercury. So these are almost planet-like in certain respects. And when we do a whole lecture on moons, you'll realize that they're just unbelievably interesting systems on their own. A lot of them have what we think are subsurface salty oceans that could also be an alternative location for life. So now we're getting to the point where we're considering sending dedicated missions to moons of Jupiter and Saturn rather than to Jupiter and Saturn in general, and so on. So, yeah. So moons in their own right are pretty interesting. I talked about asteroids and Kuiper belt objects previously, and we'll cover that in more detail later on in the lecture. But everything after moons, these are kind of the leftovers of the solar system from the times of formation. So these things are 4.5+ billion years old, which is why they're so interesting to us, because we think they are pristine leftover material from when the solar system formed, without which we wouldn't have a pretty good idea of how the solar system has formed. We'll talk about comets, which are slightly different looking than asteroids and Kuiper belt objects. The so-called Oort cloud, and we'll talk about others, things, short period comets versus long period comets. There's detached objects, which it's in the Kuiper belt, but it's kind of highly tilted and out of the Kuiper belt. It's not a dwarf planet yet. It's really too far out for us to. It has a 500-year orbit, and it's right now, I think, it's at aphelion, so it's really, really far away. And then finally, we have all the other stuff. There's gas and dust and rocks and random megalomaniacal billionaires who decide to fling objects into the solar system, which we won't do in detail now. Okay, so that's a roundup of the systems and of all the components, and we'll start going into them with a little more detail than we did previously, and with a little more knowledge in terms of scientific tools and other knowledge with which to analyze them in a lot more depth. Okay, moving on. Another quick rush through relative sizes. The sun by far dominates the whole solar system, 99.8% of the mass of the solar system, and the vast majority, it wouldn't be called the solar system if it weren't for the sun. Everything that's in it is gravitationally bound and dependent on the sun for energy. And then if we start zooming in, we have these three groups of planets over here. There's the outer big planets, there's the inner small planets, and even the outer big planets, there are two clear divisions where Jupiter and Saturn are, 10 times the diameter of the Earth, about 100 to 1,000 times the mass, whereas Uranus and Neptune are only about 10 or 20 times, and maybe 4 or 5 times the diameter of the Earth. So there's a clear dividing line over there, whereas all the inner ones, disregard Pluto over here. In fact, instead of Pluto, imagine the moon. So our moon, Mercury, Mars, Venus, and Earth are all similar enough that we will be studying them together. So these are all the terrestrial planets, which mean Earth-like. Terra is Greek or Latin for Earth, I forget which. Whereas all the outer planets are Jovian or Jupiter-like planets. Jove is one of the names for Jupiter or Zeus, the Roman or Greek king of the gods. Most of our detailed knowledge of all of these bodies has come from about, from the 1960s to now, so close to 60 years of satellite missions, and in the last 30 years or so, advanced telescopic observations from telescopes on Earth that have used techniques like adaptive optics, for example, to get much clearer pictures of these solar system bodies. We've sent a number of satellites. So Mercury has received Messenger recently. Venus has had Magellan, Akatsuki. We're basically peppering Mars with everything we've got. We've sent now 4, 5 rovers. A sixth one, and yet another one is on its way. Hopefully it'll launch this year, called Perseverance. It just got named. It's about the size of an SUV, so it's the biggest we've sent yet. The Curiosity rover that's pictured on the upper right is maybe the size of a smallish car. So we're getting bigger and more ambitious with the rovers that we're sending to Mars. We've also sent individual satellites to Jupiter, to Saturn, and it's only the outer planets that haven't had much love. Uranus and Neptune, Voyager 2 was the last satellite to visit them, and that was in the 80s. So we don't have much up-close knowledge of these planets that's less than 40 years old. We have some imaging from here, but there's nothing quite beats visiting the planets themselves. So Galileo, which visited Jupiter, and Juno, which is there now, and Cassini, which visited Saturn, gave us unbelievable amounts of data about those two planets, not to mention beautiful, beautiful pictures and wallpapers that you could basically have one new one for your desktop nearly every day, and just gorgeous, amazing images of those two planets. So astro porn at its best. And we just sent a satellite that started analyzing Pluto about a couple of years ago, then went on to a Kuiper belt object and so on. But those are the high profile missions that get all the, that get a lot of publicity and stuff. But there's ones that have gone to smaller bodies, like one called the Dawn mission that went to Ceres and Vesta in the asteroid belt, and another one that has visited, there's been at least a couple. There is the European mission that not only visited and orbited a comet, but put a lander down on one of them, which is unbelievable. There's been sample return missions that have returned samples from comets by flying through the tail and trapping particles of the comet in what's essentially a fancy flight trap, and then sending that flight trap back to the Earth, making sure it survives re-entry, doesn't burn up, lands somewhere, tracking that little package that has come from many millions of miles away, and then analyzing it in the lab. So unbelievable work. And then the Japanese have done some phenomenal left field-ish missions where they've again orbited comets or tried to bounce off a comet or send an impactor into a comet to blow up a piece of it so that they can analyze what's on the inside and so on. So some really cool missions that have gone to these smaller bodies that don't get as much publicity as the big, the oohs and the ahs you get when you see yet another picture of Saturn, for example. Okay, what did I just put up there? Okay, I think that's the New Horizons mission picture that went to Pluto and Charon, its moon. So here's a summary, an extremely busy summary of all the missions that we have sent. Obviously, the Earth is the most visited by satellites because we're on it and we keep sending satellites to them. The Sun has a whole bunch of satellites now that are observing the Sun, and we'll talk about why that's important, especially now that we've gone to a highly electronics-based lifestyle. What happens when the Sun starts misbehaving and sends charged particles our way? So electronics depend on the electromagnetic spectrum, duh. And the electromagnetic spectrum, if you remember, depends on accelerating charges, so accelerating electrons and so on, that are under our control. Now, what happens if some pesky source of unwanted charged particles, like the Sun, suddenly sends a huge blast of them our way, and way more than we can produce on our puny little planet with our puny little capabilities, and then basically disrupts all of our carefully controlled electromagnetic waves that we're using for communication and GPS and so on. So it's important for us to monitor the Sun up close and to get some advance warning, ideally a day or two before we think some major event is going to happen. We've sent a bunch of missions to Venus and Mars, obviously, because they're both A, close by, and B, seem to have Earth-like capabilities. Venus is known as Earth's twin because its mass and its orbital distance and its radius is all roughly the same as the Earth. But it's this absolutely greenhouse gas-laden hellscape, which may be a lesson for us. We shouldn't be heading that way. And Mars, on the other side, is much smaller, much thinner atmosphere, but we're still planning to land on it and colonize it and so on, I guess. There's no life there. Are we really colonizing it? We're just going to go plant a flag on it or whatever. So there's been lots of missions to both of those planets to study them because of this interest and because they might once have been habitable. There's an interesting hypothesis that if Mars and Venus had swapped positions, then they would both still be habitable with liquid water and so on. But so there may be cautionary lessons over there, or some people think it's a planet B, but it's not. I'll put up the talk on the Canvas site about why there is no planet B. We better take care of the one we have. So hopefully by learning more about these, we will learn more about how we should take care of our own planets too. There's been tons of missions to the moon. There have been a whole bunches to asteroids, comets, and so on. Mercury just got one. Jupiter and Saturn have had a few. Uranus and Neptune have just had the one, Voyager 2, which I told you about. And this one lists Titan as well, which is Saturn's moon, which is kind of an interesting place to visit, so on. Anyway, so these are all the missions that have made it out to the various large and interesting bodies in the solar system, broken down by country as well. And here's one example of what it takes to get out there. This is the Galileo mission that went out to Jupiter, and notice that it has to do a bunch of loops of the inner solar system, and each of those is basically a gravitational slingshot. It's the equivalent of being on a roller coaster where you basically go all the way to the top and then go deep down in a well and come shooting back out to gain some speed. So basically what we're doing here is, imagine in this gravitational well experience, so suppose you launch off Earth and you get out of the well that's represented by Earth. If you now go past Venus and basically go down that gravitational slope from Earth to Venus and then fire your booster at the right minute so you get out of the well, it's the equivalent of being on a roller coaster where you're trying to get a gravitational boost, so you don't have to carry as much fuel to get to the outer solar system, which is why this spacecraft did a bunch of loops of the inner solar system. So you'll see Earth fly by, you'll see Venus fly by, and so on, and then basically did a flyby through the asteroid belt and then out to Jupiter finally. And mainly that is so that you don't need as much fuel to get out there, because Jupiter is far away, 5 AU, so 5 times the Earth-Sun distance. So a minimum of 4 AU when things are lined up, but when you do loop-to-loops like this, then the distance is much larger, obviously. So once it got there, Galileo did cool things like dropping a probe into the atmosphere of the planet, and of course that atmosphere is so hellish that the probe burned up almost right away, but for an hour or so we got some amazing data about the cloud tops, or at least the outermost upper cloud tops of Jupiter and so on. And it raised, like any good science, it answered a few questions, but it raised way more questions as we got to know more about the planet than we had before, and allows us then to guide our thinking and say, okay, what should we focus on now? Similarly, the Cassini spacecraft that went out to Saturn, it ended in 2017. I think I'll put up the PBS documentary, which is called Death Dive into Saturn, which tells you all about the amazing science that this mission did. And of course, the fact that it lasted for something like 17 years means that the people working on it, the scientists, basically developed this amazing attachment. It almost became a living thing. And then when it was crashed into Saturn deliberately, again, to get to know more about the outer cloud tops of Saturn. And here is the reason why we didn't want an uncontrolled, when the fuel ran out for the satellite, we didn't want it to be wandering around in an uncontrolled fashion, because we think that Titan and Enceladus and maybe 1 or 2 other moons of Saturn may be places where life could evolve. And so we don't want to have this Saturn be a satellite, not Saturn, be tumbling around over there and then smack into a moon in an uncontrolled fashion, because there are really hardy organisms on Earth, like bacteria or something called tardigrades, that can last. They can go dormant for years and basically not need anything like water or oxygen or anything. And then if this spacecraft were to crash into one of those moons and find a hospitable environment, we don't want to infect that environment with Earth pathogens, or not pathogens, but Earth bacteria or Earth tardigrades and so on, and then go back 10 years later and go, hey, we found life on this place, and go, oh, wait a minute, this is our trash. We caused this kind of thing. So we want to be able to, so this spacecraft was burnt up in the upper atmosphere of Saturn rather than have it crash into, and effectively it got sterilized and pulverized and so on, as opposed to having it crash onto a moon where there could be the possibility of life. Speaking of that, so Cassini basically did the same thing. It did a bunch of loops of the inner solar system and then went out to Saturn. Jupiter is 5 AU away, Saturn is 10 AU away. So double the distance. So a couple of loop-to-loops. And then The cool thing about this satellite is that it sent a lander onto Titan, which is one of the moons of Saturn, and sent a probe all the way through the atmosphere and had it land on the surface of Titan. So you're seeing a mountain range in the lower picture as that lander descended through the clouds, and then when it landed on the surface, on the right, you're seeing what looks like a riverbed with these rounded, eroded pebbles. Here's the freaky thing about this. The flowing water, or the flowing liquid, is probably methane or ethane, like gasoline. It's flowing gasoline, and those rocks are all ice boulders, and probably not water ice. They're probably methane or ethane or other complex carbon compound ice, because the temperatures are so low on the surface of this planet, minus 100 degrees Celsius or whatever, that all of these processes that we're used to happening at so-called room temperature on Earth are happening way colder temperatures with completely different chemicals and liquids and solids and so on. So that's the freaky thing. So if there's anything surviving there, it's going to be something that we can't even imagine would be living on the surface of the Earth. Think about that for a second. That's just cool and freaky, So more questions than answers when that went out. And like I said, here are a few more missions. Here's Voyager 1 and 2. That really kickstarted the whole planetary exploration thing. I think I'll put up a documentary about the Voyager missions on the Canvas site, so you can look at it in your own spare time if you're interested. And one about Saturn as well. They're both, I think there are Nova or PBS documentaries about them worth watching. So the bottom ones, and this is how I got interested in astronomy, because growing up in the 80s, basically you'd get newspaper reports of these satellites and pictures of things like Saturn and Jupiter and so on. And it's just amazing. They're still active. Voyager 1 and 2 are still alive. They have both reached what we think is the outer edge of the solar system, basically something called the heliopause, meaning the boundary at which the sun's influence stops being felt. So helio from sun and pause meaning the end or stop. And we think they are now officially in interstellar space. We have very good reason to believe. They're ridiculously far away. It takes 12 hours to send a message out to them and 12 hours to get one back. So 12 light hours away. They're the most distant objects known to sent by mankind, humankind out there. And they're still going strong for a while at least, we hope. The power from each of these, you need these gigantic radio dishes to basically communicate with them, because the electromagnetic signal that comes back from Voyager 1 and 2 is so weak, it's the equivalent of a snowflake falling on a radio dish. So picture that. It's that weak. We can still detect it, and we can still find out things like, what is the magnetic field like out there and so on. The upper one shows you 5 objects that are either outside the solar system or on their way out. So Pioneers 10 and 11 actually were launched before the Voyagers. They were sent roughly in the plane of all the orbits of the solar system. New Horizons is the fastest traveling spacecraft we have ever sent. It went past Pluto, it went past the Kuiper belt objects, and now it's barreling on its way out of the solar system and will pass Voyager 2 in a few years. And so it will end up being the most distant object in a little bit. The Voyager 1 was sent out of the plane of the solar system, whereas Voyager 2 is still roughly in the plane of the solar system. So after it went past Neptune, Voyager 2 basically went out of the plane of the solar. Voyager 2 continued. Voyager 1 went past Titan, which is a moon of Saturn, and basically was the first to flag that Saturn's moon Titan is an interesting object, and then basically was turned and sent out of the plane of the solar system. I mentioned New Horizons. Like I said, even though Pluto got demoted, once we went past it, this was basically going at thousands of miles per second or per hour, and turned its cameras around on Pluto and went click, 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 click. Took a whole bunch of photos, really amazing images of Pluto, and then, there's almost a tinge of regret. This is almost like, seeing your ex and your ex is doing really well. It's that kind of thing. Well, no, this is science. Everyone was happy. That Pluto is an absolutely fascinating and interesting world in its own right, where there's all kinds of interesting stuff happening. It has an active geological surface. There's smooth parts, there's mountainous ranges, There may even be ice volcanoes, you know. So all of this stuff is happening, but again, at temperatures that are ridiculously cold. So this is all happening, you know, these are all cryo processes, but there's still some kind of geology happening that is resurfacing parts of the planet or raising and lowering parts of the planet because of things moving around on the surface. So again, raised way more questions than it answered on our way out. Answered a bunch of questions like what is the actual mass of Pluto? What is its diameter? What is its big moon, Charon, like, and so on. Okay, so as you can see, there's been a whole bunch of missions of various types that goes by. So New Horizons, for example, is a flyby. There's an orbiter, basically, like Cassini and Juno and all of them orbit the planet. They need way more fuel because once you get out there, you have to slow down so that you can fall into the gravitational well of a particular planet. So not only do you need fuel to get there, but once you get there, you have to fire your rockets in the opposite direction of your travel so that you can fall into the wells, say around Jupiter or Saturn and so on, and then start orbiting like its moons. So like Io and Europa and all of those, notice that they're partway down the well of Jupiter. So orbiters tend to be bigger and have to carry more fuel than just a flyby, like New Horizons. And then if you have a lander or a probe, then that detaches from your base spacecraft and then lands on the surface of the world that you happen to be exploring. And then there's sample return, which is another league higher of complexity. Like I said, there's sample returns from, well, we returned samples of the moon, but we sent humans there to do that. But we are planning, when we start mining asteroids, for example, we'll need bulk sample return from there. I told you about the comet sample return and so on. And the costs of these and complexity in some ways also increases from top to bottom. Okay, so our knowledge of the solar system basically is based on a lot of satellite observations and a lot of telescopic observations that we have recently. So that was a brief overview of all the satellite observations that have happened so far. Okay, so when you are looking at the solar system as an alien visitor, for example, from Alpha Centauri, then this is what the orbits look like of most largish bodies that you could account for. You'll notice that all of the planets orbit the sun in roughly the same plane, meaning they're all essentially in the same pancake-shaped structure. A little bit of variation above and below that plane, but pretty much roughly in that same plane. And then there are some objects that absolutely do not stick to that plane, like Pluto and Haumea and Eris and Makemake, and you'll notice that those are all the dwarf planets. And well, Ceres is in the plane in the asteroid belt, for example. But all of these dwarf planets have highly elliptical orbits. A lot of them are tipped in and out of the plane that the main major planets orbit in. Most of the planets have broadly circular orbits, except for Mercury and Mars, which you might be able to see are kind of elliptical. But at this scale, all the planet orbits look pretty close to circular compared to the dwarf planets. And then there's two broad classes of planets that I told you about as well. So, zooming in on the 8 major planets and the biggest, or the first major dwarf planet, Pluto. One of the things, like I said, you'll notice is that all the planets orbit in the same direction. So if you happen to be looking at it from above or below, depending on however you want to define above or below in space, there is no above, below, left, or right. Maybe there is a left and right, but no above and below. If you happen to be looking from such that this looks like a bullseye, so all the orbits are perpendicular to your plane of vision, then essentially, or your line of sight, I should say, not plane of vision, then all the orbits of planets are in the same direction. So they're all counterclockwise or all clockwise, depending on your perspective. Like I said, they all have mostly circular orbits, and you'll notice that there's 2 broad classes of planets. The inner 4 are small, they're rocky, they're Earth-like or terrestrial, and the outer 4 are more gassy or icy, and they're Jupiter-like in their composition and behavior and size and so on. If you look at it from the side, again, you'll see Pluto is well outside the plane. At this level of scale, all the planets roughly look like they're in the same plane. And notice that all the orbits look pretty much circular, except for Pluto as well. Okay. Now, not only is the revolution or the orbits of all of these planets in the same direction, for most of them, the rotation around an axis is also so-called prograde, meaning they rotate in the same sense as they revolve. So if, for example, you're looking at it from one perspective over here, the Earth looks like it's revolving counterclockwise around the sun. It's also rotating counterclockwise, and that's why you have effects like the solar day versus the sidereal day and so on. So the sidereal day is shorter than the solar day because the Earth moves a little bit in the same direction and then has to rotate more to get to the sun directly overhead and so on. Okay, there are two notable exceptions. Venus is retrograde in its rotation, meaning that over here the orbit is counterclockwise, but Venus's rotation is clockwise. So we have to account for that and figure out, okay, why is Venus clockwise and the others are not? And the other thing is Uranus is kind of strange as well, in that it looks like it rotates nearly on its side. So all of the planets and all of the dwarf planets all rotate or spin about an axis running through them. And in most cases, the direction of that rotation is the same as the direction of the revolution. Okay? So they're mostly prograde. Venus rotates backward. Uranus and Pluto have strange rotations, and they both have an axis that's kind of tipped nearly on its side. And you can see that more clearly in this diagram, where the axes of rotation and their tilts are more obvious. You'll notice, like, say, for example, Earth has its characteristic 23.5 degree tilt in the upper part of the diagram. Mars is slightly more tilted, so we talked about what happens when the tilt changes. Venus has an axis that is not tilted, and whereas all the other planets shown above, Mercury, Earth, Mars, and even the Sun, basically go counterclockwise, Venus does not. And then when you look at the outer solar system, you'll notice that Uranus basically is leaned so far over that it almost has a 90-degree axial tilt. Whereas Jupiter doesn't have one, Saturn has roughly a 20-ish degree tilt, Neptune has one too, and so on. But Uranus is completely strange in this regard. So we need to account for all of that. So we look at all these interesting patterns and we say, okay, how can we construct a hypothesis about the formation of the solar system that then takes into account all of these facts? The fact that all the planets orbit in nearly the same plane, that they all go around that plane in the same direction, that most of them also rotate in the same direction. The sun rotates about its axis in the same direction as the planets revolving. And so, taking all of that into account, we conclude that, they basically formed out of the same cloud of gas and dust that happened to be spinning one way, like I was going to say a CD or a vinyl record, but you probably have no idea what I'm talking about. So I'm going to say like a spinning platter. So any spinning platter, like a potter's wheel. Wow, I have to resort to technology from 2,000 years ago, 5,000 years ago to make this point, as opposed to something from 10 or 50 years ago. Interesting times. Okay. So the idea is that there was this one spinning cloud of gas and dust that all of these form from, which is why they're all spinning or revolving in the same direction, and the sun is also rotating in the same direction as that original cloud of gas and dust that formed them. And this is so far the most successful model of the solar system, and it's called the Nebular hypothesis because it posits that all of the sun and all of the planets and everything else left over formed from a spinning cloud of gas and dust, which is also called a nebula. Okay? And so what do I mean by most successful model? That it explains most of the observations that we see. Obviously, it doesn't explain things like, why Uranus is knocked over on its side, or Venus is rotating in the opposite direction from everything else, but we have to sort of build in special exceptions for those or figure out evidence for things that explain that. But we think for the most part, all of them form from the same cloud of gas and dust that all happen to be spinning one way. Okay. But to get to fleshing out that whole theory of the cloud of gas and dust and so on, we have to start all the way from the beginning, which is the building blocks of that cloud of gas and dust, which is the atoms. So we talked about atoms when we talked about light interacting with matter and how each atom basically has an ID that is given to it by its number of protons. So the number of protons gives it its name. So hydrogen has 1 proton, helium has 2, lithium has 3, beryllium 4, uranium has 93, iron has 26, and so on. As soon as you can count the number of protons in the nucleus of an atom, you know what atom that is. Okay? The number of neutrons can change, which is why you have isotopes. The number of electrons can change, and you get ions. But, okay. One thing about this graph is that the abundance of these elements is given in an exponential scale, so the scientific notation stuff that you did early on in the beginning. So, for example, the relative abundance of hydrogen is 10 to the 11 times, so 100 billion times more hydrogen atoms than lithium atoms. So for every 10 lithium atoms, you will get 100 billion hydrogen atoms in the universe, for example. So the vast majority of atoms in the universe are hydrogen and helium. Okay? And so by this thing, for every carbon atom, there's 1,000 atoms of hydrogen in the universe and so on. Because 10 to the 9 versus 10 to the 9 is a billion, 10 to the 12 is a trillion. So 1,000 times more. That's what this graph is showing, which is why it looks. If we showed them in regular numbers, you wouldn't be able to see anything from lithium to zinc because the y-axis would be huge. Okay, so all the hydrogen in the universe was formed at the Big Bang when the universe started. Most of the helium came from the Big Bang as well. A lot of the helium afterwards was basically formed in the centers of stars, like our sun, which is fusing or combining atoms of hydrogen to form helium inside the cores. And then when the star dies, it seeds the universe around it with the elements that it forms in its core. Most of the ones beyond that, like carbon, nitrogen, oxygen, and so on, are formed in the cores of really, really heavy stars. So 10 times the mass of the sun to 100 times the mass of the sun and so on. And these big stars kind of live fast and they die young. So they burn super bright, so they use up their fuel much faster than smaller or lower mass stars. And when they die in spectacular explosions called supernovae that send all these elements that have been made inside the star, like carbon, nitrogen, and so on, up to iron, that's made by nuclear reactions inside the star, send it out into the surrounding, what they call interstellar space, meaning literally the space between the stars, and then seeding it with these heavier elements that can be used by later stars or later gas and dust clouds that then form stars and planets and so on. Everything beyond iron gets formed during the explosion itself. So if you happen to own any gold or platinum or something like that, that was formed while a star was exploding. In the split fraction of a second that a star was exploding, it formed all of those elements. If that isn't unbelievably cool, you're not human. I'm telling you now. So all of these, so maybe you'll hold them to be doubly precious, but then why stop at just gold and platinum and silver? Everything beyond iron is kind of precious, like cobalt and nickel and copper and so on, was formed while a huge star was exploding. Okay? And then when that happens, again, those elements get thrown out into the interstellar space around, and then basically material gets recycled. So interstellar space is the ultimate recycling factory. So you start like you do on the upper left with a cloud of gas and dust that then collapses under gravity. Parts of it light up to form stars. There's nuclear reactions happening in the center of the star which carry on for billions of years. So once a star is formed, which happens within a few 100 million years, it's a few in the lifetime. So the sun has a lifetime of roughly 10 billion years, and we'll do this in more detail when we talk about the sun. But the first few 100 million years or so are spent collapsing from this gas and dust cloud into a star. And then when nuclear reactions start, basically the star starts emitting its own light and it becomes recognizable as a star. And then that continues for billions of years, well, hundreds of millions of years for really big stars, but billions of years for stars like the sun, and tens of billions of years for even smaller stars, smaller than the sun. Okay? This is slightly misleading. The sun is not going to do what you see in the lower left picture. A much higher mass star will do what happened on the left. The left is something called the Crab Nebula, which nebula is a cloud of gas and dust. This was a supernova of a really massive star that was recorded in human history. In the year 1054, Chinese astronomers, Japanese, Korean astronomers, Indian astronomers, Native American astronomers, Mesoamerican astronomers, anywhere with a native population that happened to be looking up at the heavens could see this explosion. It was unbelievably bright. It could be seen in the daytime. It probably outshone the Milky Way galaxy for a couple of days for some alien astronomer looking at it, or well, yet to see it, because it only happened about 1,000 years ago. So for Andromeda to see it, they'll see it 2.5 million years from now. Okay? And it'll probably look brighter than the entire galaxy briefly before becoming this remnant called the Crab Nebula that we see now. So the green, for example, is oxygen, the reddish stuff is hydrogen and so on, and that gets blown out, and this is several light years across. So that cloud is slowly expanding and essentially putting heavy elements like carbon and oxygen, the stuff that you and I are made of, into the interstellar space where it can be gathered up into clouds of gas and dust, and the process can start again. So the interstellar medium is basically this thin filament-like collection of gas and dust filled with all these heavy elements that previous stars that have died have created and sent out over there. And then individual pieces of that nebula will start collapsing under its own gravity and forming several stars. So I think this one shows you the Pleiades star cluster, which you can see on any given night. It's sort of this question mark shaped object that's high in the sky in the northern hemisphere. And you can see stars that have formed, and then there's dust reflecting the starlight that's around. So if you look at this with a pair of binoculars, you notice that the stars are kind of in a hazy environment, just like the Orion Nebula, for example. Okay, so about 4.5 billion years ago is when a nebula that had been created, that had been seeded with elements like carbon all the way up to uranium by some other star that blew up nearby, that started collapsing and forming what we now know as the solar system. How do we know it was 4.5 billion years ago? It's by this process called radioactivity, again, which we'll do in more detail when we study the Earth. But the quick overview of this is that when you have atoms beyond iron that have isotopes with a lot of neutrons, so as you get more protons in a nucleus, remember that like charges repel. So all those positive charges jammed into the nucleus will start wanting to fly apart. And you need to add more and more neutrons, basically, to modulate the effect of all of that repulsive force. And then there's other short distance forces called the strong force that keeps an atomic nucleus together. Well, we don't need to worry about that. But the thing is that as you add more neutrons and create these other complex isotopes, the nucleus becomes unstable. And you get to a point where then it spontaneously starts breaking apart. So uranium has 93 protons, but there's uranium-235 that has 142 neutrons, and there's uranium-238 that has 147 neutrons. And one of them is way more unstable than the other and will spontaneously break apart and release protons and neutrons and electrons and so on in a process called radioactive decay. Okay? And so when something starts decaying, basically it goes through this characteristic process where after a certain period of time, only half the original element will remain. So if uranium, for example, is a starting element, if it starts giving off protons, its ID has changed. If it's lost protons, then it's no longer uranium because it doesn't have 93 protons in the nucleus. It probably is thorium, or uranium will eventually decay into lead. So by measuring how much uranium you have, say currently, and the rate at which it's decaying, you can then back project that to say, okay, how much uranium was here in the past for it to get to this point now. And these are experiments you can do in the lab, and you can measure something called the half-life of radioactive isotopes, meaning unstable isotopes which spontaneously give off protons and neutrons and split into two smaller daughter atoms that have different element names. And so for example, a radioactive nucleus with a half-life of 100 years, basically 1/2 of that will disappear after 100 years. So if you start out with 10 grams of some object that has a half-life of 100 years, after 100 years you'll have 5 grams and then a bunch of other daughter nuclei. After another 10 years, you'll have 2.5 grams, because half of the 5 grams will then go down, will be there after 100 years and so on. And so it's this characteristic curve. You can now use elements like uranium and all that have billion-year half-lives, which is why nuclear reactions and their waste products are such a big deal, because those things stick around. If you have something with a half-life of 1 billion years, then if you start out with several kilograms of uranium that can cause all kinds of radioactive damage, 1 billion years from now, you'll still have many kilograms of the stuff lying around. So that's why we have to deal very carefully with radioactive waste. So that's one way. And the second way you can do it is by doing things like counting craters. Early on in the solar system's life, when there were a lot more fragmented bodies flying around, they basically hit a bunch of other bodies, like the Earth, for example, or Mercury, or the Moon, and so on, and what was called the late heavy bombardment. Essentially, there were so many small bits of rock flying around that there were craters everywhere, and that happened around 3 billion years ago. So if you see a surface with a lot of craters, you can sort of safely assume, yeah, this is about 300 billion years old. 3 billion years old. What am I saying? Okay, so like I said, rocks have, if they have radioactive elements in them, have half-lives, and the material basically can then be backtraced to how much used to be around before, and you can start timing how much. So these are some elements where if you see some samarium-147 lying around and there's neodymium nearby, you can measure how much there is of each. So samarium basically loses 4 protons to become neodymium, for example, and half of the samarium is still around 100 billion years later, for example. Like I said, uranium-238 has a half-life of 4.5 billion years, not just 1 billion, like I said before. So that's roughly the age of the solar system. So by measuring how much uranium and lead is in some rock sample, you can figure out, okay, how much uranium was there and how old is this rock sample as a result. And that's why we have such a pretty good idea that the solar system is a minimum of 4.5 billion years old, because we have found rocks that we can date back to that time period. Okay, so for our theory of solar system formation, we think the solar system formed from a cloud of gas and dust that already had a lot of heavy elements in it. I mean, the majority of the cloud of gas and dust was hydrogen and helium. 98% hydrogen and helium, 2% everything else, which is everything else is lithium to uranium, which all form naturally in stars. Okay? Out of that 2% is what the Earth and you and I and everything else on it formed, and all the other rocky stuff as well. The vast majority of the cloud was gas, 99%, and 1% of it was dust and ice. And that 1% dust and ice is critical, because we think that in the environment that the Earth formed, in the early days, it was too hot for water to stick around. It probably would have just boiled away into steam and gone away, or broken up from the intense radiation environment around. And we think comets or asteroids from the early days of the solar system that still had ice basically may have seeded the Earth with water during the late heavy bombardment when they slammed into the Earth. So water may have been brought to the Earth later on, well after it formed, so that it reached the Earth at a time when liquid water or water vapor could exist on the planet and not just get blown away or boiled away and so on. Okay? So this roughly spherical cloud collapsed on itself from just the gravity, mutual gravity between all the particles, and there are plenty of simulations showing you this on YouTube, for example, and then basically flattened into a spinning disk from conservation of angular momentum, which we talked about early on. Okay, so it contracted, and as it contracted, it was rotating, and this one rotation direction basically ended up governing the direction in which planets revolve, the direction in which they rotate, and the direction in which the sun rotates. Okay? The center of this nebula is basically what formed the sun. So the nebula broke up, it collapsed, it spins, and we see this in other stars and systems. We see this happening from a number of scales. So the galaxy, our galaxy, for example, we think formed similarly. Started out from a collapsing or growing clump of gas and dust, and ended up becoming this pancake-shaped spinning structure. Stars and planets form that way. The environment around planets also breaks up. Once planets form and clear up some of their orbit, the environment around planets also ends up looking like this, with a thick central bulge and a disk around it, which is how we think Jupiter, for example, looks now like a mini solar system. So this process happens at many, many scales. And like I said, it happened about 4.5 billion years ago by mass, 98% hydrogen, and helium, 2% everything else. And basically, yeah, the sun was formed by gravitational contraction of the center. How do we know that this might be true? We have seen this around other stars. So here's a picture of another star with the central star blocked out because it's too bright and it overwhelms the brightness of the disk. And you can see a disk of gas and dust around it. And we've seen many, many, many instances of this. So this disk of gas and dust is way larger than the size of Pluto's orbit around the sun. Okay? And here's a whole menagerie of stars just in the Orion Nebula. So one nebula a few thousand light years away from Earth, maybe a few hundred. I have to look this up. But it's relatively close by, and these are all stars that are currently forming in that nebula. And each of these images basically shows a circumstellar disk, or a disk that's around a star orbiting very young stars. So these are stars that are a few 100 million years old or so. And these are all seen from different angles. Some are glowing. The gas and dust is glowing because they're lit up by a nearby star, like this one. Others are dark because you're seeing gas and dust absorb light. So you're seeing it against a bright background. And so each of these basically looks like our solar nebula and are potentially locations where planets are being formed right now as we speak. Okay? And this random table basically shows you what percentage of the mass. I don't know why it's here, but the central bulge of the disk has the bulk of the mass, and then the planets have some tiny fraction of the rest. Okay, so this is the visual side of the evidence that the solar nebula hypothesis is a good one that might explain how we formed. The second is the chemical side, where Jupiter and Saturn are these gas giant planets that have a lot of hydrogen and helium, just like the sun. They're roughly the same composition as the sun, so could they have formed roughly at the same time? And again, in the Orion Nebula, we see examples of stars that have central stars and then disks that are essentially forming out of the same material as the rest of the nebula. Okay? And so some things like the fact that these hydrogen helium rich gas giant planets are only in the outer parts of the solar system is a good indicator, because we think hydrogen and helium are the lightest elements. They may well have been just blown away by the sun's heat and radiation. And we can also see other disks where there are gaps close to the star, and then there's actually a lit disk slightly further away from the star. Or we can even see evidence like the one in the upper left, where this is further along in the planet formation process, and each of those dark rings is a place where a planet may have started accumulating gas and dust and pebbles and rocks and debris and starting to form, and then cleared out its orbit. So that's highly suggestive on the upper left, and on the upper right, there's a whole bunch of other images showing stars that have cleared out parts of their disk as well. Okay? And so we think that planets basically form similar to how these stars form. When you have a large nebula, pieces of the nebula start collapsing, they flatten and they spin to form a disk. And so you can have many of these disks embedded, like you saw in the Orion Nebula, just a couple of like this or like this. And in each of those individual disks, you could have pieces of that disk again collapse and flatten and spin in miniature again to form planetesimals, or the seeds or the beginnings of planets, which is why, say, Jupiter looks like a mini solar system, and so does Saturn, and so on. And so grains of dust and ice and gas, dust and ice basically collide and stick. And then once this seed of a planet or a planetesimal gets to a certain size, it can start growing pretty rapidly and clearing out its orbit, basically sucking up everything like a vacuum cleaner in its orbit as it goes around in this spinning disk. Okay? So there's this feedback process. As the mass increases, the gravitational force increases, so even more stuff gets glommed on to this forming planet. And on the upper right, there's an image where now we have an object that's bright enough because it's collected a whole bunch of material close to the star, and we see what we think is the beginning of a planet in the image on the upper right. And so all these inner planets, or planetesimals, were mainly made out of rock and other debris, whereas the lighter stuff, like the gas stuff, got blown into the outer solar system where it could be collected by Jovian planets, for example. And then where Uranus and Neptune formed, it's far too cold for there to be sort of puffed up gas like you see in Jupiter, and instead they basically collected ice and rock to form out there. So these lumps essentially grow into planetesimals and protoplanets. So we have the visual side of the evidence, we have the chemical side of the evidence, and now on computers we can also simulate solar system formation. And this basically start with a clump of gas and dust and see what happens when we set it in motion. And these take supercomputers and really heavy-duty computer simulations to actually perform. But we see similar-looking structures as the solar system forming. Now, when we study extrasolar planets, we have basically had to revise a lot of our theories of planetary formation because we've noticed in those observations there's a lot of Jupiter-sized planets really close into their star where we didn't think should be possible. In fact, for some techniques, the vast majority of planets that we find are hot Jupiter-like planets that have formed very close into the star. So they're gas giants really close to the star, basically getting blasted by stellar radiation, and we've had to revise our planetary formation theories based on those observations. But the solar nebula theory, for the most part, does a good job of explaining a bunch of things in our solar system, like why is the bulk of the mass in the sun, why do Jupiter and Saturn, for example, why are they close to the sun in composition, why do all planets and the sun rotate in the same, revolve, why do all the planets revolve and why do the sun rotate in the same direction, why do most of the planets rotate in the same direction as they revolve, and so on. A lot of those phenomena are well explained by this nebular hypothesis. Okay. Some things that the simulations also notice is that in the process of formation, there's all these collisions and migrations that can occur. So maybe those collisions can explain why Uranus, for example, has been knocked over on the side. It probably got whacked by a large body and got knocked sideways, literally. Why Venus, for example, also may have been hit. So there's a bunch of things. And why, say, a rocky planet like the Earth, which is not that big, has one of the largest moons in the solar system. All the other large moons are around gas giants or ice giants, not around a planet as small as the Earth. And as we saw, the fact that we have this large stabilizing moon is something useful when we think about why life may have evolved on the Earth and not elsewhere. So it's worth thinking about how things like our solar system doesn't look like others in the sense that the rocky planets are close to the sun in a zone where liquid water can exist, whereas in other solar systems, we're seeing really hot Jupiters close to the sun and so on. Okay? So that's the process. So those are the three lines of evidence. The visual, where we saw pictures in places like the Orion Nebula, the chemical side, which looks at the compositions of various planets here and elsewhere, and now the computer side of things. So let's go on to actual planets and describe what they're like before diving into more detail with some of the other categories of objects. Right, diving into our solar system. There are currently 3 known classes of planets. Well, ones that we have constructed ourselves. There's the Jovian or Jupiter-like planets that I said, which are gas or ice giants. There is no real viable solid surface. Parts of them may be solid deep in the interior, but anything we send in to try and get there would basically be destroyed, pulverized, unrecognizable, probably wouldn't even be able to communicate out and so on. So for the most part, we say there is no solid surface. And take that with a pinch of salt. Okay. They're far from the sun, basically beyond the asteroid belt, beyond what we will call the ice or the frost line, basically beyond a line in the solar system. Beyond that line, it's too cold for liquid water to exist in any form. They're mostly made up of hydrogen, helium, and compounds of hydrogen and carbon. So they're, at least Jupiter and Saturn are a lot like the sun. They all have rings around them and many, many moons. Many in the sense greater than 10, perhaps. And in the case of Saturn and Jupiter, greater than 60, 70, and so on. The inner planets are all, and will include the moon here. So in fact, I should go through and basically scrub Pluto from all of these slides and include the moon with Mercury and Mars and Venus and the Earth. They're closer into the sun, so all the lighter stuff like hydrogen and helium got blown away. They're small and rocky, so they're surfaces that you can physically stand on or land on. They're mostly metal and rock. So metal and rock are made up of elements that are beyond carbon, nitrogen. I mean, they're compounds of carbon and oxygen as well, but they're actually magnesium and iron and silicon and aluminum. So heavier, denser materials. So they are much denser than the outer planets. They have no rings, none of them have rings, and they have pretty few moons, 1 or 2 maximum. I think Mars has 2, Earth has 1, Pluto has 5 or 6. The rest, the rest have none. The dwarf planets, they're all smaller than Mercury. There's 1 or 2 that are nearby, like Ceres, and most of the rest of them are TNOs, or Trans-Neptunian objects, meaning objects beyond the orbit of Neptune. There are some components of rock, but a lot of ice and various ices. They could be water ice, they could be ammonia ice. So basically ice from compounds of carbon, nitrogen, hydrogen, oxygen, and so on. And they could have moons. Some Pluto does. When we get to the dwarf planet slide, we will see that 1 or 2 of the others have them as well. The main dividing line for a lot of these objects is their density, meaning how much mass they have per unit volume. So if we were to construct an equation, the density is directly proportional to the mass. The more mass you have, the denser you are, and it's inversely proportional to the volume, meaning if you have a higher volume for the same amount of mass, then your density goes down. And the reference we use for high density or low density is water, because it's one of the most familiar substances to us. By definition, we have constructed this such that water has a density of 1 gram per centimeter cubed. And you'll see that with a lot of other things, like temperature scales used to be tied to the properties of water, where 0 degrees Celsius is the freezing point, 100 is the boiling point, and so on. So whether or not these bodies are denser or lighter than water, denser or less dense than water, is a key dividing line. Um, Between Mars and Jupiter, somewhere past the asteroid belt, is where this dividing line is most obvious or likely to be situated. Jupiter, Saturn, Uranus, and Neptune all have densities roughly around the density of water, or a density of 1. In fact, Saturn's is less than 1, so if you can imagine a ginormous ocean that is much bigger than Saturn, Saturn would float in it. It's essentially this big fuzzball, and that's a technical term as well. So if an object has an average density, meaning its total mass divided by its total volume, an average density that is higher than that of a fluid that it's sitting in, then it will sink. So metal, for example, a hunk of iron or steel, if you put it in water, its average density is greater than 1, and it will sink. But when you create a shell of iron and steel, and then build other stuff in it, such that the interiors are, say, some iron, some steel, a lot of air, and some plastic, and call it a ship, then the average density of that ship, which is the entire mass of that ship divided by its entire volume, which includes all the air in it, which is much lower in density than water, if the average density of that happens to be lower than water, then it floats. And so that's why you have these big hunks of steel, but with a lot of air in them and a lot of lighter materials like plastics and so on, floating on water. And before we could do that, a lot of ships used to be made out of wood, which has an average density less than that of water. Ooh, forgot to silence my phone. Okay. So the inner planets are made of rocky materials, and they have very dense iron cores, for example. And so they have much higher densities, or much higher average densities, than water. So they're 3-5 grams per centimeter cubed, for example. In fact, I think Mercury is amongst the densest planets out there. Whereas the outer ones are primarily composed of light elements like hydrogen and helium, so their average densities are much lower. So this dividing line of density is one that we will use fairly often to characterize these planets, and where we start making these distinctions between terrestrials, gas giants, icy bodies like in the Kuiper belt, asteroids, and so on. That's not necessarily in order of density. As you can imagine, Jupiter and Saturn have the lowest densities, then probably Uranus and Neptune, then maybe Kuiper belt objects, then asteroids, then planets in increasing. But there's variations amongst all of them. So the giant planets we already looked at to some extent. They're mostly hydrogen. The rest of it is mostly helium. That's for Jupiter and Saturn. So they're very close to the sun in composition. The sun is like 90+% hydrogen, and the rest of it is helium. Actually, way more than that. Okay, I'll have to double check this before we do the sun lecture in the first place. Okay. They may have cores that are kind of liquefied hydrogen, which is why maybe the no solid surface argument stands. They have unbelievably spectacular looking clouds and surfaces and raging storms across them. Neptune and Uranus are much further out in the solar system, so it's much colder over there. So when gas gets cold, it tends to occupy much less volume. If you heat it up, if you heat up a balloon, for example, it starts to expand. So they have much lower volumes. It's also because it's so cold, you can have molecules and compounds of carbon and hydrogen and nitrogen and so on existing out there. And these ices tend to be a little more dense than the stuff that makes up Jupiter and Saturn. So they form beyond this ice line. They have the majority of the planetary mass, and their orbits keep getting bigger, and their periods or years keep getting longer. Because they're slowly sort of climbing out of the solar well. We'll talk about that in more detail when we get to these planets and study them in more detail. The 4 terrestrial planets, Mercury, Venus, Earth, and Mars, and the Moon, we study together. They're made up of elements that are way down the periodic table. So carbon, nitrogen, oxygen, magnesium, iron, silicon, aluminum, and so on. That were made in the centers of massive stars or made while those stars were exploding. These dense materials, the interesting thing, and so like we said, there's a density dividing line between inner planets and outer planets and so on. There's also a density dividing line in these bodies themselves. They are what we call differentiated, meaning the densest parts of these bodies are at the center, and the stuff that's on the outside is actually lighter stuff. So the rock that you see on the outer part of the Earth, believe it or not, is less dense than the stuff at the center of the Earth, which is, we think, is a liquid iron core, which maybe even a solid iron core down in there as well. And iron is a pretty dense material. And so so this is called differentiation, where a body is segmented by density, where the densest stuff is in the middle and the less dense stuff is on the outside. So that differentiation is very common amongst a lot of rocky and icy bodies. And that gives us a very important clue. Differentiation does not happen when the body is solid. It can only happen when these atoms or compounds can move around freely, and that happens when the body is a liquid. So, we think, because these bodies are differentiated, that they were liquid or extremely hot at one point, and the differentiation happened when they were liquids or extremely hot, and the denser stuff fell to the bottom, just like you have oil and water. Water is denser than oil, so the water ends up on the bottom and the oil on the top. Or like icebergs and water, for example, ice is less dense than liquid water. So that differentiation happens when these bodies, or happened when these bodies were liquids, and that's a key part of the formation theory as well, that they probably formed in a much hotter environment than other things, other undifferentiated bodies like Kuiper belt objects, for example. Okay, so these bodies are mostly made out of rock and metal. Any water or ice that they might have on them was most likely delivered later on by asteroids and comets that came from the icier, colder parts of the solar system. I should rearrange this so that the ice line stuff is actually before all of this. Sorry about that, we'll get there soon enough in a few slides. Okay, now, like I said, here is the density table in the right column. Mars, Earth, Venus, Mercury all have densities well above 3 or 4 almost. These are average densities, which is their total mass divided by their total volume. And like I said, Earth and Mercury are amongst the densest planets, whereas all the outer planets have densities close to the density of water, which is 1, and in Saturn's case, it's well below 1, for example. Okay, so the 4 inner planets are relatively small. They have high average densities. They're rocky. The 4 outer planets, they have large diameters, 50,000 to 140,000 kilometers, whereas the inner ones, the Earth is the largest, 13,000 kilometer diameter. The outer planets have low average densities, and they're mostly hydrogen and helium. And here's a bigger table to put all that together. This is in your textbook as well. It gives you densities, it gives you composition, it gives you things like rings and moons, basically summarizing all the stuff that I talked about in the first few slides. So this is a summary of the 8 planets that we know of. Yes, I did say that we know of because there's always theories being put forward that there may be another mysterious planet 9 way out there that's perturbing orbits in the outer solar system and so on. Okay, leaving aside these 8 main planets, there's the dwarf planets as well, and there's about 5 officially recognized dwarf planets, one of which is in the asteroid belt, Ceres, and the remaining 4 are in the outer solar system beyond the orbit of Neptune for the most part. Pluto is sometimes inside the orbit of Neptune, and it's the discovery of Eris that basically caused this whole class of planets to be created, because Eris was realized to be roughly the same size as Pluto, roughly the same orbital characteristics, and so on. So people are like, we should either make Eris a planet or create a separate class. And these 5, basically the ones that do not dominate their orbits, they have highly elliptical, usually highly inclined orbits as well, are the officially recognized dwarf planets. Okay. Only Ceres and Pluto have had, so the Pluto one, this is an older slide, this is before New Horizons. Pluto should have crystal clear, amazing pictures that the New Horizons missions delivered. Ceres has the Dawn mission pictures as well, so we have detailed pictures of Ceres. All the other three are essentially kind of artists' conjectures, and hopefully someday we will get to them. Okay, so the gravity is sufficient for all of these objects to draw them into spherical shapes. But you may be looking at this saying, but what happened to Haumea? Okay, so Haumea, if it were not rotating or rotating much slower, would be spherical. But if you look down at its rotation period, all the others have rotation periods that are on the order of 1 to a few Earth days, whereas Haumea does not. It has a rotation period of just 6 hours. And so because it's rotating so fast, its material is less dense than Ceres, and it's been pulled into this oval shape because of the centrifugal forces that are acting on it. Ceres is much denser, and even though it rotates in only 9 hours, basically its stuff is not flying apart like Haumea's is, and so it is still spherical, whereas Haumea is not. But Haumea, had it not been rotating at that high rate, we think would be spherical, which is why it's been classified as a dwarf planet. So the earliest one of these to be discovered was Ceres in 1801. There was a prediction that there was a big gap between Mars and Jupiter where there should be a missing planet. Ceres was discovered, but then they went ahead and discovered a whole bunch of other bodies as well in what became known as the asteroid belt. Pluto is about 20% of the mass of the moon, even though it's about 2/3 of the diameter of the moon. It has a large moon called Charon. And so this may actually, and we think that Charon may actually be another Trans-Neptunian object that was captured by Pluto. And these two are large enough that they orbit each other rather than one orbiting the other. So Charon causes a pretty significant wobble in Pluto's orbit because of the gravitational attraction that it has. Eris has a highly erratic object. It's kind of Pluto-sized. It caused the demotion of Pluto. It has a moon called... So Eris is the goddess of discord. Basically, she caused all this chaos every time she showed up. And so because the planet classification system got shaken up, it was named Eris. Makemake is maybe Pluto-like. We don't know a lot about it. And the other interesting body that's not here is a moon of Neptune called Triton, which is roughly the same size as these bodies, and we think it's a captured Trans-Neptunian object. It may be more massive than Eris or Pluto. We also think that one of these objects may have whacked, an object like one of these may have whacked Uranus, which is why Uranus is orbiting on its side. So those are all the planets and the dwarf planets, and a good chunk of these dwarf planets are actually in a belt called the Kuiper belt, which is also known as sort of Trans-Neptunian objects, or the home of Trans-Neptunian objects beyond the orbit of Neptune. So all of these objects are in, like I said, something called the Kuiper belt, which is what we think is a reservoir of completely pristine icy bodies left over from the formation of the solar system, so all 4.5 billion years old. And that's why they're really interesting bodies to study, because we think they reflect the composition of the solar system at that time while it was forming. Pluto and this snowball-shaped object on the left called Arrokoth, or Ultima Thule, were visited by the New Horizons spacecraft on its way out through the Kuiper belt. And so those are the only two that have real photographs taken. Everything else here is kind of made up, or an artist's conception of what they might be. If Ceres was out in the Kuiper belt or amongst these TNOs, it would be between Sedna and 2002 MS4. So Sedna and Quaoar are these really elongated objects that make highly inclined orbits in that area. So the Kuiper belt, rather than being a belt like the asteroid belt, which is mostly flat for the most part, some variations here and there, the Kuiper belt is more like a donut. It's kind of this donut-shaped ring around the outside of the solar system, or at least around the outside of Neptune's orbit. And it, along with a spherical cloud that's even further out called the Oort cloud, we'll talk about that in more detail when we talk about comets, we think is the source of a lot of comets, which are these icy bodies that come in from the outer solar system on these highly elliptical orbits, go around the sun, and back out again. And so we think comets with short periods around 100 years or less, come from the Kuiper belt, and the ones with longer orbits come from this Oort cloud, which is the spherical shell of even older, not even older, but really old icy bodies as well. So we think that these bodies can provide sort of very valuable insight into the birth of the solar system. Some of the solar system models say that, oh, these objects were formed where they are right now and didn't move. Others say, oh, they might have been migrated out. They formed closer in and migrated out when Uranus and Neptune formed and cleaned out the orbits around them. Analyzing these objects may solve that question, because then we can go analyze one and say, oh, does this look like an inner solar system object or an outer solar system one, or is it a unique class of objects by itself? So they all have highly tilted, highly elliptical orbits. That's why the Kuiper belt is more like a donut rather than the asteroid belt. So Ultima Thule, or Arakoth 486958, the snowman-like object on the left, is the furthest object that has been visited by a satellite. It's something called a contact binary, meaning we think these two big, roughly spherical objects collided and stuck. And it's the most primitive object in the solar system that's been visited by a spacecraft as well. So I encourage you to read up on it. There's also a talk that was given at Foothill College early on that talks about Ultima Thule as well. I'm not really sure how to pronounce it. I haven't really watched any Marvel movies or anything. But regardless, Thanos and all those guys don't live out here. So nothing to worry about. Okay, finally, that ice line that I've been talking about, or the frost line. I really should be moving this slide well before all of the planetary stuff. But that's kind of this density dividing line as well. Inside the line, you can have liquid or water vapor exist. And you have rocks and metals that can condense. Beyond the line, it's mostly hydrogen compounds. Within the line, when the solar nebula is still forming its central star or planets and so on, most of these compounds are gaseous. Outside it, you can have ices and compounds and rocks and so on condense, and then a lot of migration and collision happens. We think the temperature of the disk is pretty high, roughly 1200 degrees Celsius, but it decreases with distance from the sun. Within about 5 AU, so within Jupiter's orbit, many compounds can condense out of the gas phase, like water and carbon dioxide, and not carbon dioxide, water certainly. Things like water and ice and so on basically came in later on from things that were beyond the frost line and then made it in close to the sun. And so essentially, this is what it looks like inside and outside the frost line, where rocky planetesimals can basically accrete and form terrestrial planets close to the sun, whereas beyond the frost line, it's mostly rock and ice combinations. Okay? And so, like I said, here's the 5 AU boundary, where we think roughly this frost line is, and then beyond the orbit of Uranus, you can even have ice made up of other complex compounds of carbon and hydrogen, or organic compounds like methane and ethane and so on. Okay, so that gives you a roundup of these objects that independently orbit the sun, but don't dominate their orbits. There's also moons around a lot of these big planets, and around our own as well, that are kind of worlds in their own right. A number of them are bigger than planets, like Mercury, and certainly bigger than Pluto, for example. And so that's why they are interesting objects to study in their own right. So they're comparable in size to Mercury. I don't have the actual size of Mercury here. Maybe I'll have to go back. Let's see, diameter somewhere between 2,500 and 5,000 kilometers. Where is Mercury? Mercury has a diameter of about 4,800. There we go. So 4,800 is the diameter of Mercury. And so there's at least two moons, Ganymede and Calypso, that are bigger than Mercury. Three, Ganymede, Callisto, and Titan, which is a moon of Saturn, that are bigger than Mercury, and a bunch of others that are pretty close in size as well, like the Moon, Io, and Triton, and Europa as well. Okay? And so each of these has very interesting both geology and characteristics, and ones like Europa and Ganymede and Triton we think might even have subsurface oceans that could possibly harbor life. And Titan, like I said, has this unbelievable set of lakes and rivers and so on, but the flowing liquid is liquid methane or ethane, essentially flowing gasoline-like liquids on the surface. So some of these outer moons are differentiated. They're big enough because they're bigger than Mercury and so on, so they're differentiated when they form. So their cores are much denser than the outer parts of it. The outer parts are hard ice. So Ganymede, Callisto, and Titan are basically composed half of frozen stuff like ices, some of it of which is frozen water ice, and half of it is rock and metal. But they're also very, very cold outer crusts. And it's so cold that the ice behaves like rock. So you can have what looks like geological processes like ridges and so on forming because the ice is so cold that it behaves like a rock. And we even see that on places like Pluto and so on, which is why you can have interesting geology with really, really cold ice as well. So just finishing up the accounting of the other stuff, there's rings around the outer planets. Those, there's a number of hypotheses on what they might have been, how old they are. For example, we don't think Saturn's rings are that old, so they're not the age of Saturn itself. They may be far more recent, which is why they may be busted moons, for example, or material from moons that are ejecting material, like Enceladus, shown in the middle of the top row, whereas the others may be leftover debris or not. So, yeah. So, but Jupiter, Uranus, and Neptune don't have rings that are as spectacular and crazy as Saturn does. Okay, so that's an accounting of all the stuff so far. We're now going to go into a deeper dive on some of the original material, like comets and asteroids and trans-Neptunian objects, before we start going into planets and dwarf planets and their moons later on in the course. Right. So we said there are these three interesting regions of objects that are the sources of the objects the homes or the sources of the objects we'll be studying. So asteroids, which are between the orbits of Mars and Jupiter, are mostly metal and rock because they're inside that 5 AU line where rocky stuff accreted. There is the Kuiper belt, which is beyond the orbit of Neptune. So a lot of rock-ice combinations, basically. Ooh, I didn't mean to go there. I meant to go here. So there's rock-ice combinations where the Kuiper belt is, which is to the extreme right of the image, over here. And the asteroid belt is kind of where the frost line is, but on the rocky side of the frost line. So you have two different interesting regions where we'll be studying slightly different objects with mostly rocky versus rock-ice combinations. And then there's the Oort cloud, which I talked about, which is also, we think, a source of comets that make it into the inner solar system. These are all considered the debris of the inner of the solar system because, again, the vast majority of the mass is in the sun, and then most of the mass of what's remaining is in Jupiter, like this slide showed you. So comets and asteroids basically take up around less than 1/10 of 1%. So they're around, what am I saying? They're about 0.06% of the mass of the solar system. But they're still vital. Without asteroids and comets, we don't think we would have had water on our planet, for example. another thing to add to your whole list of what made life possible on this planet. Okay. So like I said, leftovers of formation from the solar system. There's 3 distinct debris fields. The asteroid belt, they're small and dense. The Kuiper belt is beyond the orbit of Neptune. The Oort cloud is hard to see. It's really far out. We don't really yet know if this exists, but doing simulations of comet orbits makes it seem like such a thing should exist, which is why we think it's out there. So it's a massive sort of spherical debris field of comets that's around the sun. Okay, so starting with the asteroid belt. Like I said, they're small and irregularly shaped for the most part, except for Ceres, which is not considered an asteroid anymore. It used to be for the longest time until, say, the early 2000s. If you add up all the mass of all the asteroids, it's less than even the mass of the moon. It's like 1/30th the mass of the moon, all of them combined. And there's different types of them. They are either continuous rocky bodies like you see in the upper left, or they're ones that look like accretions of pebbles. So several even smaller bits that have just kind of cemented themselves together. And sometimes they're either dull gray, or sometimes they have interesting colorations, like the asteroid on the lower right. Like I said, here is a comparison of the Earth's moon with the top 7 largest asteroids. We have visited Ceres, we have visited Vesta, and I think Hygeia has had a visit as well. Yeah, so Ceres had a dedicated satellite mission sent to it, that and Vesta as well, the 2 biggest asteroids. Ceres turns out to be this really interesting body. There's some amount of cratering. They found these mysterious white spots that are in a lot of craters. And we thought, okay, maybe they're ices of sort of salty compounds, maybe ammonia compounds and so on. It doesn't have too many craters, which means it's not that old. So parts of this planet, this dwarf planet, have been resurfaced. It has a thin atmosphere from outgassing ice, so it's kind of an interesting body in its own right. There's even a 3-mile tall mountain. So 3 miles is roughly the height of, say, Mauna Kea, 15,000 feet, for example. And we think it might have been a volcano at some point, but a cryovolcano, meaning the stuff coming out of it was liquid ice, not liquid rock. Like I said, rock can be cold enough that it can behave like, ice can be cold enough in some places where it behaves like rock. And then, so maybe this object formed somewhere else and migrated, we don't know. So there's an artist's impression of the Dawn mission on the lower right. Okay. So asteroids, though, are not just located in the asteroid belt. There are various places that they can be located in. The primary location, the majority of them, are between Mars and Jupiter. Their diameters could be, around 1 meter, which is less than the size of a person, all the way to 1,000 kilometers. And the vast majority of them are closer to 1 meter and 10 meter in diameter than to 1,000 kilometer. We know about 500,000 of them. We track a lot of these asteroids because we think that Jupiter's gravity can sometimes perturb them and knock them into the inner solar system when they cross the Earth's orbit. And when they do cross the Earth's orbit, it becomes a problem because some of these are big enough that they can cause damage down here. So the question is, what are these? They could be failed planets. They could have stayed in the planetesimal stage. We have some theories of what they might be. Okay, yes, here's a diagram showing you the various zones. The white ones are in what we call the asteroids belt. There are a couple called the Greeks and Trojans that are attached to Jupiter's orbit. There's an interesting location in Jupiter's orbit that we'll talk about where the Jupiter and the sun's gravitational pull balance each other out. And so asteroids have congregated there as well. There's a few in the inner solar system between Mars and the sun, so some of those are marked in red, and those are the ones that we track and care about. And there's yet another zone called, I can't read it over here. The Hildas, it looks like. Okay, so there's about 4 or 5 different zones in which asteroids can exist. The majority of them are in the belt itself. How do we think they ended up the way they did? There are 3 of the many types, there are three broad classes of asteroids called M, C, and S. M stands for metallic, so meaning we think that those might be the cores of planetesimals or asteroids that were destroyed. So meaning that these were differentiated asteroids. So differentiated means they must have been heated high enough to liquefy, then differentiate, then get destroyed. And so these are the remnants of the ones. So anyway, the top 1 through 5 basically shows you the cores. So 1 through 4 is stuff accumulating or accreting, all these pebbles. Once it gets large enough, it may have got hot enough to liquefy and then differentiate in number 5 in the formation slide, and the formation part of this diagram. And then destruction, basically collisions and impacts, break them up. And the M-type ones are the leftover blue cores, or pieces of cores, of differentiated asteroids. And the S and the C are from the outer regions, we think, where S stands for stony or silicate. So they're somewhat undifferentiated, so they may either be primitive, meaning they never differentiated, so they never heated up to the point where they differentiated, or they could be from different parts of differentiated asteroids that broke up, and we don't see the other layer, so they're only a piece of the outermost layer, or only a piece of a middle layer of an asteroid. And finally, there's also carbonaceous, which is basically compounds of carbon, also undifferentiated, also we think either primitive or a piece of a differentiated asteroid. So these three broad classes of asteroids. Okay, so that's how we think they formed. Why did they end up where they did? Jupiter basically is the dominant gravitational influence on these asteroids. And we notice that there's a surprising lack of asteroids in zones where the asteroids have a multiple of Jupiter's orbit. So if Jupiter has, I don't know, an orbital period, well, now that we have the handy-dandy table, let's go look it up. Jupiter has an orbital period of 11.9 years. Let's call it 12 years. Okay? So remember, the Earth is 1 year. Mars is about 2 years. So all of these asteroids have orbits roughly between 1.5 and 3 years. Sorry, what am I saying? Between 2 and 12 years. 12 years is the orbital period of Jupiter. So now if we take an orbital period of 12 years, then 1/4 that orbital period is a 3-year orbital period. So somewhere between Mars and Jupiter. So where it says 1/4 on the x-axis down there, you'll notice there's a whole bunch of them missing. Where it says 1/3, so 1/3 of 12 is a 4-year orbital period. There's a bunch missing. Then there's other multiples like 2/5, and then of course there's 1/2, which is a 6-year period, and so on, and 3/5 and 3/4. So these are all not coincidental. This orbital resonance phenomenon we'll see a lot when we talk about moons of the outer solar system and so on. But the point is that these multiples, or these whole number fractions, that's not even a mathematical term. Okay, these fractions that are some multiples of, not random multiples, but very specific ones, like 1/4 or 1/2 or 3/4 or 2/7, for example, of Jupiter's orbit, there are asteroids missing because of this crazy gravitational interaction that happens, because every now and then the asteroid will line up with Jupiter. So if it's 1/4, then every 4 orbits, it's lining up between Jupiter and the Sun. And I'll show you a video of resonant orbits as we, you start out the Sun, the asteroid, and the Jupiter in one line, and Jupiter starts moving. 3 years and a bit later, they'll line up. Then 6 years later, they'll line up. Then 9 years later, they'll line up. And 12 years later, they'll line up. And so that, at each of those periods, some crazy gravitational interaction happens and basically perturbs the orbit of the asteroid and knocks it out of its orbit into some other orbit that is not an exact multiple like this, where they don't line up on a regular basis. Okay, and despite these diagrams showing you extremely dense fields, it's not like Star Wars. the asteroid belt is still pretty empty. Most of these are thousands to hundreds of thousands of kilometers away from each other, which is why Star Wars sucks. The science is horrendous. You never have like spaceships going through these fields of rocks and debris where they're likely to bump into one, and Han Solo or Luke or Chewie or someone has to be extremely careful going through them. Watch Star Trek. Much better science. There's way more books talking about the science inspired by Star Trek than Star Wars. Star Wars is absolute crap. And it's also owned by Disney. Strike number 2. And it took them a while to include things like strong female characters and characters of color. Strike number 3. If you're watching Star Wars, you're a horrible human being. Okay, rant. I'll turn off the rant now. Lagrangian points. Like I said, like these Greeks and Trojan asteroids, the whole class is usually called Trojan asteroids. Those are at points in Jupiter's orbit, so they're in the physical orbit, or they're orbiting around small parts of that orbit, called Lagrange points, where the Sun and Jupiter's gravity basically balances the centrifugal force that these objects feel at that point. And it's something that we use here as well. If you remember from the last lecture when I talked about telescopes, like the James Webb Space Telescope is going to be orbiting what's known as the L2, or the second Lagrange point, for the Earth-Sun system. So what we're seeing is the Sun-Jupiter system and Lagrange points where there are asteroids. L2 in the lower right diagram is again a place where the gravity of the Sun and the Earth balances the centrifugal force that something feels at that point, which goes outward. So the gravity is pulling inward, whereas the centrifugal force is pointing outward. So you don't need much fuel to keep a satellite at the L2 point, and that's where the James Webb Space Telescope is going to be. There's other satellites at that point as well. There's ones at the L1 point between the Earth and the Sun, and they are observing either the Earth or the Sun. It's a good place to do that. There's ones at L4 and L5, which are taking 3D views of the Sun, because they're taking it from two different, so it's like having two really widely separated pairs of eyes. Okay, end of that digression. But, so like I said, there's a lot of impacts and collisions in the asteroid belt that shape the asteroid belt itself, break them down into smaller asteroids, and also determine what type of asteroid it might be. Some of them can collide with each other and get knocked into orbits, or Jupiter itself can perturb them out of resonance zones and send them towards the Earth, and some of them will hit the Earth every now and then. So 3 to 3.5 billion years ago, there was a much heavier bombardment of the Earth when there was a lot more of this stuff floating around. But thankfully for us, they're less frequent now. However, we still have something to be thankful for in terms of asteroid strikes. Mammals as a whole class of animals would not have grown to dominate the Earth had it not been for an asteroid that wiped out the dinosaurs 65 million years ago. If that asteroid had not hit, we would still probably have dinosaurs roaming the Earth and dominating, and we would still be sort of our ancestral form, which are these tiny, scrabbly little animals that lived underground for the most part, and as a result probably avoided the terrible effects of this asteroid strike, because most mammals at the time, our ancestors, were mole-like creatures that lived underground for the most part. So be thankful for things like rats and rodent-like creatures, because that's what ended up probably spawning us. This is not obviously an exact genealogy, but you should do some more research into that. Anyway, so the reason we have mammals and sentient mammals here is because an asteroid strike wiped out the dinosaurs 65 million years ago. Previous asteroid and comet strikes may have carried water. We definitely think carried water to our planet and made life possible. It's also possible that bacteria evolved first in places like Mars at a period of time when Mars had water and Earth did not. And a meteorite from Mars may have landed on Earth, carrying bacteria with it, and seeded life on Earth. Not inconceivable. There's something called the panspermia hypothesis that says that life originated elsewhere in the solar system and then landed on Earth where it found a hospitable environment because it arrived at the right time. After all the bombardment was done and when bacteria could take hold over here and so on. Anyway, basically a physicist helped with putting forward this hypothesis of the asteroid stripe, because where you see the dime in the upper left picture is a thin layer of this radioactive element called iridium, which you see between rock that is older than 65 million years and rock that is younger than 65 million years in age. And so for the longest time, people were trying to figure out what is this boundary of rock that we see everywhere in the world. It's called the KT boundary, which is between the Cretaceous and the Triassic period. I think there's a more modern name for it. You'll have to look that up. Okay. But basically, a physicist helped with decoding what this boundary was. And then finally, they were looking all around. So the Earth undergoes erosion and things. And they finally found the location of what they think is this crater, which is off the Yucatan Peninsula in Mexico. And so there's a whole row of cenotes, or sinkholes, that are in the porous limestone of this peninsula, which define what we think is the rim of this crater boundary, or the rim of this crater, I should say. There's so there's a trough in the land inside of that rim, and the rest of it is underwater. But even if we do underwater mapping, we think we see remnants of this big boundary of a crater. However, now that we are here and established, we don't want what happened to the dinosaurs to happen to us. And so sure as hell, we keep track of all asteroids or space rocks that can hit the planet. So over the entire history of the Earth, we think so far we've found evidence of about 150 impact craters that could have caused catastrophic collisions, meaning widespread damage and probably widespread extinction, which fortunately hasn't happened in the last couple of billion years, one or two maybe. But before that, there were a lot more. And today, an asteroid or a meteorite that's large enough to cause damage, it strikes a building here on the Earth about once every year or so. And declassified military satellite data shows that a 1 meter sized asteroid hits the Earth maybe once a week. So the question is, what would we do if an asteroid that's large enough to, say, destroy a city, which could be 10 or 100 meters across, was found to be headed towards the Earth? And so there's something called the Minor Planet Center that tracks several tens of thousands, hundreds of thousands of objects that you see in the green and red. Most of the green ones in the lower left are in the asteroid belt. Most of the red ones are the ones that are inside the inner solar system and may cross the Earth's object at some point. So we sure as hell keep track of these to make sure that we're not going to be wiped out like the dinosaurs anytime soon. But the question is, are we at the point that we know what to do? If an asteroid were to the size of something that killed the dinosaurs, which is probably much smaller than the radius of this crater. So the crater is several kilometers wide, the Chicxulub crater, but the object that created it was maybe a kilometer, which is pretty small in the grand scheme of things. If it were headed our way, what would we do? We have one answer. We send Bruce Willis up there in a spacesuit, bring him out of retirement, and send him up there and go plant a nuclear bomb and blow it up. Maybe. If it fails, it may create like 2 or 3 chunks of asteroid that are now headed towards us that can still destroy cities and so on. Should we do things like send a satellite up there and slowly nudge it out of the orbit? Send it into orbit around the asteroid if we know early enough. Launch a satellite, nudge it into a different orbit so it misses the Earth. Anyway, interesting things to think about. So that's asteroids.